Today we will be starting with the second chapter of your textbook, that is work, energy and power. Alright, we'll be learning about one by one all of them, that is what is work, what is energy, and then what is power. So let's start with work. Okay, now what is work? Right now that you are sitting and you're listening to the lecture, are you doing any kind of work? Yes or no? Yes, you're working, right? You're using your brain. Yes, Irene, you're not doing any work. Nothing is entering your head, no? Yes or no? We are sitting here, you're trying to understand things, you're trying to work your brain out. Yes or no? So we are doing some work. But let's understand what is the difference between work in real life and work in physics with an example. Alright, so imagine that there's a lady and her job is to, she wants to move this wall. Move as in shift this wall away. Alright. So what does she do? She hires someone, a constructor, and she tells him that you need to move this wall. Okay, now what the person does? He starts applying force on the wall. Yes, in order to move it, he's applying a force.
One eternity later.
This woman comes back and she notices that the wall is still there. But look at the man. The man is tired because whole day he has been pushing the wall and the wall did not move. Okay, but he became tired and he says, I have done my work. I need my money. So if you were the lady, would you pay him?
No.
No. Why not?
Because there's zero displacement in the wall.
Okay, that's good. You wanted the wall to be displaced. It is not displaced. So why should you pay him the money? But then the worker's logic is, see, I have tried and I tried my best. I pushed it, but I couldn't do. So the worker has also spent time, right, in doing the work. Then shouldn't he be paid? Well, that's the difference between work in real life and in physics. Okay, see, in physics we don't want any ambiguous answers. In physics we want that if the work is done, we should be able to see it. Yes or no? The lady came and the lady saw that the wall has not moved. So maybe that guy is just acting, right? He never worked only. So if she cannot define the work in terms of physics, then we do not say that the work is done. All right, let's understand how do we define work in physics. So work is said to be done only when a force applied displaces the body. Two things. First thing, force must be applied. Second thing, the body must be displaced. If the force is not applied or the body is not displaced, like in this example, we say the work is not done. Is that okay? So a force must be applied and there must be a displacement. So that's the definition of work done. Now, so what are the factors that affect the work done? How do we increase the amount of work done or how do we decrease the amount of work done? Very good. First will be the force, right? More force you apply, more work will be done. So we can say work is directly proportional to force. What does it depend on? That's a very good answer, but it does not depend on time. We'll learn about it, why it does not depend, but work has nothing to do with time. Even if you do it fast or you do it slow, we don't care, okay? Okay. Then what else does it depend on?
The displacement.
Of course, it depends upon the displacement. So work done is directly proportional to displacement. But it also depends upon the third thing, that is the angle between the force and the displacement. Is it fine? So work depends on three things: force, displacement, and the angle between the force and displacement. All right. So what will be the formula of work done then? The formula of work done will be, this is important, you can note down, force into displacement into cos of the angle between them. All right. So what will be its SI unit? Its SI unit will be Newton meter or joules, and cos theta does not have any unit, so we will not be writing anything here. Then what will be its CGS unit? Its CGS unit will be dyne, centimeter, or erg. So let's imagine something like this, okay? Do you know what this is? What is it called? A lawn mower, all right? In a lawn mower, when you push it like this, right? What is the direction of the force that you apply? In the lawn mower, in which direction do you apply? We apply it in the downward direction, yes or no? So we apply the force in this direction, downward direction. But does the lawnmower go inside the ground? No. The displacement is in this direction. So do you see that there is an angle between force and the displacement? Right? So this angle also we'll have to take into account when we calculate the work done. Alright, let's calculate the work done for this. So work done will be force into displacement into cos of theta. So how much is the force in this case? 5 Newton. S is 2 meter and cos theta is cos 45. So this will be 5 2s are 10. Does anyone know the value of cos 45? 1 by?
1 by 2.
1 by root 2. So then I'll just keep it like this only for now. I'll not rationalize. So it will become Newton, meter or joules. Okay. Now what are the special cases? So when we say special cases means in terms of theta. So the first one can be theta is equal to 0. That means the angle between the force and displacement is 0. All right. So for example, look at Peter Griffin. He's falling off the sky. All right. So in which direction will be the force? It will be in the downward direction. So force is in the downward direction, and since he's falling also down, the displacement will also be in the same direction. So same direction means theta is 0. All right. Another example can be when you lift a suitcase up. When you're trying to lift the suitcase up, you need to apply the force in which direction? Up. And the suitcase will also move up. So it's in the same, force is up, displacement is up in the same direction. Okay. Can you give me an example? Ananya. Walking. Walking, in which direction you apply the force? Forward. How are you walking? Ananya? Ananya has forgotten how to walk. Great. Irene? Very nice. Suitcase, school bag. So smart, Irene. I'll take that. I'll take that. Yes, DJ.
And taking water from that well, the building water is
If you are not using any pulley, like if you're pulling it like that, no? Yeah. But if you're using a pulley, then you apply the force in the downward direction, no?
the water.
Huh?
So the bucket of water which goes down.
The bucket of water that you lift like this. And that's what. So suitcase, bucket of water, bag, school bag.
Sir, I have a question.
Yeah. When you kick a ball, opening a pen cap. Yeah. So when you open a pen cap, you apply the force in this direction. The cap also opens in the same direction. Okay. Enough of examples. In this case, we say that the work done is positive. Very important for MCQ and all. So when is work done said to be positive? When the force and the displacement are in the same direction. But what about this case? When theta is 180. Theta is 180 means the force and the displacement is in opposite direction. Means you apply the force in the forward direction, but the body is moving in the backward direction. Can you think of any example? You apply the walking. You see how ideas get stolen? Yes, walking. When you walk, you apply the force in the backward direction, but you move in the forward direction. Yes or no? Okay, next time you walk, you think about this. Okay. But let's take some examples. Hey, again the same guy. right? He's lifting the suitcase. How? Well, it's not wrong. But here we're talking about a different force. All right. Which force are we talking about? The force due to gravity. See, when the suitcase is being pushed up, the gravity is pulling it down. Yes or no? But the suitcase is going up. So this will be the case where theta is 180. You get it? So when we talk about this, we're talking about a different force. When we talk about the previous one, we spoke about the force being applied by the man. Here we're talking about the force applied due to gravity. Is it clear? So here be very careful. The force will determine the work done. Okay. Another example can be, it's the wrong one. Yeah, it's this one. Okay, look at the guy how he's catching the ball. All right. Observe. So when he catches the ball, he applies the force in which direction? Down. If he applies the force down, he applies the force in which direction? Huh? Backward, like this. No, he does not.
If he pushes the force,
He does not apply this.
the ball. If you have to take it down so that the time will increase and you catch it properly.
Yes, very good. But he applies the force in which direction? Upward. Because if the ball is coming like this, and if you apply the force in downward direction, you are helping the force, right? So maybe it will fall much more. To resist, you have to apply the force forward, right? But as Zishan said, he doesn't apply it instantaneously. He gives it time, right? But he's constantly applying the force in the upward direction, but the ball is moving in the downward direction, right? So the angle between them is 180 degree. So in this case, we say that the work done is negative. All right. So when is work done positive? When the force and displacement is in the same direction. When is it negative? When they are in the opposite direction. All right. Now there are situations where work done can be zero also. We have seen positive, we have seen negative, it can be zero also. It's okay. I found a new feature in DaVinci. It removes all this nonsense. So when is work done zero? Can you tell me when is work done zero? Very easy. When you push a wall. So when you push a wall, how is it zero?
So,
There is no displacement. So one case can be when displacement is zero. Another case,
When there's no force.
when there's no force. If I don't apply force only, work done is zero. Another case, so I got two. When force is zero, when displacement is zero, other case will be when angle is 90. If angle is 90, then cos theta will be 0, right? So that's the third case, when cos theta is 0. If cos theta is 0, then theta will be 90, so work done is 0. Very often asked in the exam, when is work done said to be 0? Most of the time it is something related with the displacement is 0 or cos theta being 0, that is theta being 90. Then let's see the second case, that is when displacement is 0. So let's look at the first one. Look at this guy, right? He's trying to push the beam. Obviously the beam is not going to move. So displacement is 0. Okay. This is my favorite. Have you watched this? Do you know what this is? No? Wait, nobody knows what is this. Which clip is this? You're so good, people. Good, good. Yes, they're science students only.
What the hell? Look at this. Bump, 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 bump. That's work. That's home. That's work. That's home. What, this guy? He has two places every day all week.
So what he's trying to show is he's basically monitoring someone. And you see what is this guy doing?
Places every day all week.
This is home and this is work. All right. Just like how you guys are, but instead of work, you're going to school. So from home, you went to school. Then from school, you came back home. All right. So where did you start it from? Home. Where did you end up at?
Home.
So displacement is how much?
0.
So displacement is 0 means you did not do any work. Right? Say whole year you have not done any work. You were born here and after so many years also you are here only. So displacement is 0. So if you think about it, in our entire life, we don't do any work.
So when I was born, then my displacement was 0. Whereas if I'm nearby an hospital, my displacement can be 0 kilometers.
Yeah, basically if you were born in the hospital and if you end up dying in that same bed where you were born, then this extreme examples, but displacement is 0. So basically in our entire life, if you think about it, the work done is from where you were born to where you die. That's your displacement, that's your work done. Right? Rest everything is immaterial according to physics. Okay. Then another can be the earth revolving around the sun. So let's say this earth starts revolving from here. After going through all the seasons, autumn, winter, spring, it comes back here. So displacement will every time be 0 because it come back to its original place. So the work done is also 0. Alright. Now let's see the last situation where work done can be 0, that is cos theta is 0 or theta is 90. The first example can be this only, when the earth is revolving around the sun. So the force that is pulling the earth towards the sun, we know that is centripetal force, but the displacement is in this direction. So what is the angle between force and displacement? 90. Cos 90 is 0, work done is 0. Okay. Another example can be, let's say a man walking with a weight due to gravity. The force due to gravity will be in which direction? Downward. And the displacement is in which direction? Forward. So the work done is 0. Also, to lift something, you need to apply the force in the upward direction and the displacement is in this direction. So the work done is 0. Notice here that the force is very important. Which force are we talking about? Here the work done will be 0 due to the force of gravity. Of course, as Ananya said, he is applying the force in the backward direction and moving in the forward direction. That is different case. Okay. But in this example, we are particularly talking about the force due to gravity. You got it? Yes? Okay. So this is the force in the downward direction. This is the displacement. Angle is 90. So the work done is 0. Now see, in practical life, when you push a car or when you're doing a work, do you apply a constant amount of force? Or does the force change over time? How? We get tired, yes or no? Right? So if you're lifting a box and you're walking, over time what will happen is you will feel tired. Yes or no? So the force that we apply in real life is not constant, it's a variable. For example, let's say that you started really highly energetic and you applied the force of 10 Newton. Now slowly when you get tired, obviously it will drop down to, let's say, 1 Newton. Okay, finally it will become 0, but let's say 1 Newton. Now the question is, which force should we take then? Should we take 10 Newton or should we take 1 Newton to be applied in the formula? Yes or no? Right? Let's understand this with an example. So imagine you're pushing a car. All right. Let's see a graph that is force versus displacement. So along the y-axis is force, along the x-axis is displacement. So as Tanya said, that in the beginning you'll be very energetic, so your force will be very high. Yes or no? But as you start pushing, you get tired, the force will constantly decrease. Yes or no? After that you can't push only, you're so exhausted. Yes. So then how do we find the work done in this case? Well, work done in this case can be found by calculating the area under the graph. Okay, you find the area of the force versus displacement graph and that will give you the work done. Is it fine? So what is the shape in this case? Triangle. And what is the area of triangle? Very good. Half into base into height. Okay, so the base is displacement and the height is force. So half into force into displacement. That will be the work done. You got it? Okay, here we are assuming that the force is constantly decreasing. In higher classes, you will learn when the forces are not constantly decreasing also. Okay, that it's the slope will go up and down. Here we're just thinking that it's a reducing force. You got it? Yes?
So what if it's constantly increasing?
If it is constantly increasing, then your graph will look like this. Let's say you started from 10 Newton, so it will look like this. Okay, then displacement will be like this. Now the area will be this trapezium's area. This area will give you the work done. Work done will be area of trapezium. Okay, so let's move on. Now, what is the work done by the gravity? This is a very specific topic. We will calculate how much is the work done particularly by the force due to gravity. All right. So for that, let's imagine we have a ball whose mass is m and it is placed at a height of s from the ground. Okay. And let's say that the ball is freely falling under the force of gravity. So we know that the force will be mg. Now, can you tell me which scenario is this? The force and displacement is in the same direction, opposite direction, or they're making an angle?
Same direction.
Same direction. So if it is in the same direction, then work done is given by what? Force into displacement into cos theta. Force is mg, displacement is s, and cos theta. What is theta here?
0.
Very good. 0. Cos 0 is 1. So mg s, or if s is the height, then we get mg h. So work done will be given by mg h. So work done by the gravity for a freely falling body will always be mg h.
So,
Yes.
this cos theta 0.
Cos theta is 1. Cos 0 is 1. How is theta 0? So look at this. This is the direction of the force and this is the direction of the displacement. So what is the angle between the two? Okay, see, this is the direction of the force and let's say this is the displacement. Is there any angle between them? Yes. Roughly how much will it be? 30? Fine. Now, roughly 15. Okay, what about now? Exactly. So when they are in the same direction, the angle will be 0. So that's why theta is 0 and cos 0 is 1. But what if you are lifting the body? What if you are lifting this ball? What is going to change? Yes? The direction. If the direction changes, that means in the formula, what will change? The angle, that is theta, right? So what will be theta in this case? So if you are pulling it up, then the work done will be F into S into cos theta. But this time theta will be how much? 180. Yes, good. And cos 180 is minus 1. So it will become F into S into minus 1. That is minus F into S. Okay. So work done against the force of gravity is minus mg h. Nothing changes except the minus sign will be introduced now. Where are your secondary eyes? Can you see anything? SI unit will be Joule, CGS unit will be ergs, right? Obviously. And the relationship, I hope you remember, 1 Joule is 10 to the power 7 erg, right? Okay. Now let's see what is power, right? DJ, this is where what you're saying will come into play. So what is power? Imagine that we have a girl, Ananya, okay, a very strong girl, and we have a weak boy, Zishan. Okay, let's just say. And let's say that they have a piece of work, that is they need to lift 100 kg of stuff. All right, 100 kg weight by a distance of 20 meter. You got the situation? Ananya, a strong girl, Zishan, a weak boy. 100 kg has to be lifted up against the force of gravity by 20 meter. Let's calculate the work done by each one of them. So work done will be what? Due to gravity, we know the formula mgh. M is 1000. G, let's take it to be approximately 10. And h is 20 meter. So 100 will be 2 and then 1, 2, 3, 4. 1, 2, 3, 4 joules. So 20,000 joules will be the work done by each one of them if they do the work. But what will be the difference between the two? Between Ananya and Zishan, both of them, they will do the same amount of work. But what do you think will be the difference? Time. How? The one who is, say Zishan. Zishan who is weak. Why are you saying the one who will be weak? I've clearly mentioned Zishan is weak. So you'll say Zishan will take more time. Right? You say Zishan will take more time and Ananya will lift it up very fast. Yes. But remember, the work done by both of them is same. 20,000 joules. But since Ananya did it first, she will have more power. Yes or no? That makes sense, right? That since she is more powerful, she'll be able to lift it in less amount of time. Right? So what is power? Power is the rate of doing work. Rate of doing work means how fast are you able to do a piece of work. That's power. Okay? So power is equal to, what will be the formula? Power will be equal to work divided by time. Okay, let's remove Zishan. We don't need it anymore. So power. Yes, Raghav.
When it in the upward direction, right? But at times we are acting against the force of gravity, and if you do, it should be minus.
Excellent. Chocolate. Excellent. This was very good, Raghav. Good catch. Since we are acting against the force of gravity, so it'll be negative. Okay. At least one person is understanding. Your 2 chocolates are on hold. I forgot to bring. So now see, what is the formula of work? We just learned what is the formula of work? Sorry? Yeah, what is the formula of work, Zishan?
For mgh.
Yeah. F into S. Okay, I like that is also correct, but the general formula of work done is F into S, assuming that the force and displacement are in the same direction. Now, if I just take F, now what is displacement by time? Anyone remembers class 9? Displacement by time? Velocity. So velocity. So that's another formula of power. Force into velocity. So that's fine. Till here it's okay? Yes? Okay. So what will be its SI unit? Yes?
What?
Abigail, did you say something? I can't see you now because of this DJ. Who said it? Oh, what will be the SI unit?
What?
Watt. Yeah. So it's actually joules per second, or we can also say watt. Alright. Watt is the actual name. And what will be its CGS unit? CGS unit? Erg? Very good. It will be erg per second because work done is erg and time is per second. But there is another interesting unit called horsepower. Have you heard horsepower?
Yes.
You've heard where?
So my car has 195 horsepower.
Oh, which car is it?
It's XUV7 2.2 liter engine.
Very good. How many horsepower?
195.
What is that supposed to mean? 195 horsepower means what?
So I just know it's good. I searched in Google.
See, Horsepower is another unit of power. All right. Why is it so? Because if I tell you like what he said, his car is 195 horsepower. No, what would you understand from that? Like if you had to make a logic out of it, what would that mean to you?
So 195 horses running together and generating the power is equal to the horsepower.
Yeah, that's what it would supposed to mean, no? That his car is as powerful as 195 horses. Yes or no? Yes, but that is fake. Okay, let me explain you the real thing. So this horsepower is actually created by Watt. Okay, James Watt. He is the inventor of, do you know what this is? Yes, it's steam engine. So he was the inventor of steam engine. Now when he made steam engine, he if he want to convey people the power of his steam engine, right? He's want to say that my engine has 5,000 watt. Will people understand? No, because most people they don't even understand watt. Yes, no. People who take science, they go to school, they don't know SI unit is what. Yes. So how will the village people they will understand that watt means power? So what he did, right? He thought that okay, my steam engine is replacing the horses. So let me try to bring the power in terms of the horses only, right? He did an experiment where he tied a horse and he took that rope and tied it on a heavy box. All right, let's say 250 kg, and then he made the horse pull it. Okay, the horse pulled it. If the horse pulled it by a height, then we know in how much time did he pull. Let's say 1 second. Can we not calculate power of the horse using this formula? Yes or no? So this power we will get in watt, and he measured it to be 746 watt. Is it fine? But this experiment was recently done. Okay, it's in a YouTube video you can watch, and they saw that the power of horse is actually more than 2000 watt. Okay, so there can be two things. First thing, it can be that James Watt was very smart, so he intentionally reduced the conversion. Okay, that can be the first case, or second case can be that he made a mistake, which is rare given that he was so smart. You get it? So when you say that my what XUV 700, when you say your XUV 700 has 195 horsepower, that basically means 195 into 746 watt. Okay, you can calculate and you'll get how much watt is your car. Then let's talk about energy. So I think you guys know what is energy. No, you guys don't have any. So what is energy? See, energy is basically the capacity of doing work. Okay. The more energy you have, the more work you'll be able to do. The less energy you have, the less work you'll be able to do. Yes or no? Right? So that means energy is nothing but work. Okay. How I like to see it is energy is what you have before you did a piece of work. Right? Right now, if I'm not doing anything, I just ate my food, just woke up, I have full energy. Once I do the work, that energy gets converted to work. Yes, I lose my energy and I increase the amount of work. So we can say that energy is nothing but work. All right? Yes? Yes, Raghav.
So, like a person with 10, he has more energy.
A person who has,
Like with 10,
who's
10, 10.
thin.
Yeah.
Yeah. Why are you showing yourself? You're not thin. Yeah.
But a person who's fat, he has more energy.
Okay.
Energy.
Thin or fat? You're body shaming, Raghav. It does not matter whether a person is thin or fat. Okay. A fat person can also have more energy, but there are people who are fat but with less energy. Okay. Are you referring to someone? Okay. So what will be the SI unit of energy? joules, right? Since energy is nothing but work, so its SI unit will also be joules. CGS unit will be erg, and 1 joule is 10 to the power 7 erg. Bigger units, okay. Now we have a special unit called electrical units. All right, let's say why do we need electrical unit? Let's say you're using an AC whose power is 2000 watt and you're using for 10 hours, right? So how do you calculate the energy consumed? What will be the formula of energy? Very good. Power into time. What did you say? Energy will be power into time. But in SI unit, power is 2000 watt and time is what?
10 hours.
10 hours, but we have to convert it to seconds. SI unit, right? So it'll be how much? 10 into 60, that converts it to minute, into 60, that will convert it to joules. And if you calculate, you get 236, 72, and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 joules.
So in the 10 hours
10 hours, yes.
and 60 for minutes,
Yes.
50 for 12 for
Okay, I'll take care of that in editing. Okay, no chocolate for you. So that many joules. All right. So it'll be, I hope I calculated right. 1, 2, 3, 4, yeah. This many joules. Now imagine if this number shows up in your bill for using the AC for 1 day. Your mother will get shocked, right? Ah, you use so much of energy. Yes. Yes or no? And imagine that for a month. Multiply this by 30. So people will not be able to comprehend such big numbers. Do you agree? That's why we need bigger units. So one of the bigger unit is watt hour. Okay, this is the unit of electrical consumption. Do you ever use any electrical devices for seconds? Huh? Do you? Like, let's say you want to search something. Okay, you're so confused that you turn off, let's say everything is off and you want to search for something. Oh, I got it. Do you do that? No, you keep it on, right? For a very long time, we keep it on. That's why the electrical energy is never measured in seconds, right? We always choose the unit hour. Okay. Now there are two units. Either you can keep the power in watt, or you can make that also small by using kilowatt. Now see, this number looks nice, no? That, oh, only 20. Okay, it's fine. Yes or no? Rather than this number looks like a demon, but this number looks nice. Oh, 20. It's fine. Right? Okay. We have other units also. The other one is calorie. Have you heard of calorie? Calorie?
Last year,
Huh?
3050 calories.
Why did you look at him when I said calorie? I don't like those. That was so not good. Yes, Dishan, what are you saying?
Psychology.
Yeah, see, that's what it does to people. No, I'm just kidding. She was not looking at him, just making things up. So, yes, what is calorie? Where have you heard calorie? Huh? Food. Yes, when you eat food, you check calorie, no? That, oh, this much calorie, that much calorie. At this age, you don't have to. Right? So, what is exactly a calorie? For that, imagine that you have a water, 1 gram of water, that is at 14.5 degrees Celsius. A very specific temperature. 1 gram of water at 14.5 degrees Celsius. And you want to bring it to a temperature of 15.5 degrees Celsius. What would you do? We would heat it. So you would heat it. Then the amount of heat that you need is known as 1 calorie. You got? The amount of heat required to change 1 gram of water at 14.5 degrees Celsius to 15.5 degrees Celsius is known as 1 calorie. Okay? And 1 calorie is exactly equal to 4.18 joules. Roughly 4.2 we can say.
I didn't understand.
Okay. Which part? The whole thing? Okay. See, imagine that you have 1 gram of water. Okay. You have 1 gram of water, so very less. And that water is, let's say, at exactly 14.5 degrees Celsius. Okay. What I want to do is I want to increase that water's temperature from 14.5 to 15.5. So what do I do with this water whose temperature I want to increase? I would heat it. Now when I heat it, that heat is nothing but energy, right? So I have to give it some energy. So the amount of energy that I have to give, that is 1 calorie.
So basically, are the energies equal to calorie?
Yeah, the amount of energy that I have to give in this particular situation is a calorie. And it is calculated that it will be 4.18 joules. Alright. Let's see another one. This is a little bit complicated. Try to understand. Electron volt. Now, what is electron volt? Imagine that you have a negative plate here and you have a positive plate here, and here you keep an electron at a difference of 1 volt, right? So if you apply the concept of charge, what will happen to the electron? It will be pulled. It will be pulled by whom? Positive, and it will be repelled by the negative. So naturally the electron will move towards the positive. When it moves, it will gain energy. Yes or no? Any moving body possesses energy. Then the amount of energy gained by this electron is known as 1 electron volt. You got it? So the amount of energy gained by an electron under the potential difference of 1 volt is known as 1 electron volt. Got it? No. Which part? See, imagine this is the positive plate, this is the negative plate. So positive, negative. Now if I keep an electron here near the negative plate, we know that negative, negative, they repel each other. So this electron will be pushed by it and it will be attracted by the positive one. So it will be pulled towards the positive. So when the electron moves, it needs energy to move, right? So that energy that the electron will get is 1 electron volt. Okay, which is extremely less. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. Minus 19. Very, very less. Okay. All right. Then let's see the different types of energies. Now energies can be of different type. All right. Can you name these energies? What is this? What type of energy is this? Electrical energy. What type of energy is this? The whole thing.
Nuclear energy.
Nuclear.
Explosive.
This is nuclear. Hiroshima, Nagasaki is nuclear. This is dynamite. What energy is this? Chemical. Very basic. Okay. What energy is this? Solar. What energy is this? Nuclear. Yes. What energy is this?
Light.
Light. What energy is this?
Sound.
So there are different forms of energy. Let's look at how can we convert from one energy to another. So here, this is a dynamo. We will make this when we do the electricity chapter. So this is a dynamo, and here if you rotate a coil in presence of a magnetic field, it produces electric current. So when you are moving, what kind of energy will that be? Mechanical. Okay, kinetic energy, mechanical, and it's getting converted to electrical energy. So mechanical energy is being converted to electrical energy. Okay, questions are asked from here in the exam. Okay, this, now you try to guess, this is, what is this? It is a motor. So it's converting energy from what to what? Huh? Electrical to kinetic. It takes what type of energy? Current, gives out motion. So electrical to kinetic. Okay. Or electric to mechanical. What about this one? What is this? What is this? Very good. You're ruining my animations. Iron. What type of conversion?
From electrical to heat.
From electrical to heat. What is this? Okay. This is the thermocouple. Okay, what is the thermocouple? Basically, if you take two rods at different temperature. Let's say this is hot and this is cold. And if you connect them through wires and in between if you put a bulb, you will notice that the bulb glows. All right, maybe I'll show it to you someday, right? So that is known as a thermocouple, where we use the difference in heat energy to produce electrical energy. You got what I said? Difference in heat energy to produce electrical energy. So this will be from heat to electrical. Then what is this? Speaker. Here what do we convert? Yes, speaker needs electricity to work and it produces sound. So electrical to sound. What is this? What is this? This is mic. So what do we convert? Motor. It's a mic. It's a mic. It converts sound to electrical. What is this? Yeah, this one everyone knows, phone. So what are we doing with the phone? We're charging. So this stuff. Electrical to chemical. Very good. Because the phone runs on the battery, which requires chemical change. And when you're charging your phone, you're basically converting the electrical energy from the socket inside the battery's chemical energy. Okay, very good. This was very tough. What are we doing here? Very relatable for all of you. What are we doing? Texting, basically using a phone. So when you're using a phone, what type of energy conversion that is? I'll clip it off. Yes. What energy conversion is this when you're actually using it? Yeah, the battery, inside the battery there are chemicals. So those chemicals are being used to produce electrical energy. No? So it'll be chemical to electrical.
So it also produces light.
Very good. So that means one form of energy can be converted to different forms. Yes or no? So very good. Chemical is being converted to electrical. That electrical is also used to produce light, sound, and so many things. Okay? Okay. Then this one. What is this? Candle. So what to what? Heat to light. Light to heat. Yeah, but candle. What is the candle doing? Candle, if I don't burn the candle, if I just take this candle, what kind of energy does it possess? Sorry? My bad. Let's say the candle is on the ground. What kind of energy does it possess? See, center of gravity was up, so it was not stable, it fell. What kind of energy does it have now? This is the ground. Chemical, it will have some kind of chemical energy. That wax is nothing but a chemical. So it'll have chemical energy. When you burn it, that wax gets burnt. So that wax that has chemical energy gets converted to light plus heat. Okay. But more of light. Don't write heat in the exam. Okay. Nobody is sitting near the candle and light. Light is the main energy. This one. What is this? But yeah, photosynthesis. Then solar energy to chemical energy. Okay. Light to chemical. This one? Electrical energy to light energy. This one? Solar energy to electrical energy. Okay. Let's learn one interesting topic, that is degraded energy. Now, what is degraded energy? I'll take the example from what you said only. Imagine you have a candle and you're burning the candle. What is the purpose of burning the candle? What do you need? Light. So we need light. But do you get only light? You also get heat. Do we need this heat? So this heat, isn't it a waste? Yes or no? This waste only is known as degraded energy, right? So sometimes the energy gets converted to a type of energy that we don't need. That is known as degraded energy. All right. So the loss in energy while transforming from one form of energy to another desired form of energy, when you lose some energy.
So then where does the energy go?
Heat, environment. Yes or no? Like for example, when you are driving a car, right? So when you're driving a car, what type of energy do you need?
Mechanical.
Mechanical energy. But you also get other forms of energy like kinetic is mechanical only. When you rev the engine, what do you hear? Sound, right? So that means sound energy is also being produced. But we don't need it, right? The main purpose of mechanical energy. So that sound, you can imagine as if its energy is lost. So that loss in energy is known as degraded energy. You get it? Every time you convert one energy to another, there will be some form of loss in energy. Every time. Okay. This tube light, when I'm using the tube light, what conversion is this? Electrical to light. But if you touch these tube lights, they will be hot, they'll be warm. That means it's producing heat also. Do we need that? That is also degraded energy. You got it? Okay. So this is the one of the main chart for energy. Okay. That is potential energy getting converted to kinetic, and then kinetic energy getting converted to heat, sound, electrical, and so on and so forth. Remember this, potential energy can only be converted first to kinetic. Then kinetic energy can be produced so many ways. Okay, like for example, see, what kind of energy does this marker possess? As it was falling, what kind of energy did it have? See, potential to kinetic first. Okay, you cannot convert potential to any other energy. First, you have to convert it to kinetic. But once it fell on the ground, then what kind of energy did we get? Sound. So, sound energy. You got it? Till here is fine? Okay, then let's stop for today. Finally. No, Raza? So fast. Close the copy. Where's your fuzzy? Hi.